Hi everyone, welcome and thank you for joining us for our Math Hub workshop seminar. It is my great pleasure to introduce our guest speaker, Dr. Marian Gidea, who is a professor at Yeshiva University, and he has extensive experience and expertise in many applications in dynamical systems, such as selection mechanics, mathematical physics, and many other applied mathematics. Professor Gidea has contributions to the fields over the past 30 years. And today he is going to share with us one of his research in selection mechanics, which is the three-body problems and the low-energy space missions. So let me hand over to Professor Gidea, please.
Thank you very much. So it's a great pleasure to give this lecture. So the work that I'm going to present encompasses perhaps several papers. Some of them are in collaborations with other researchers. Some of them are in collaboration with students. And I'm going to mention these collaborators as I go on. And I also included here the NSF logo because some of this work has been supported by NSF grants. So I'm going to start with the motivation of this work. So one of the motivation is concerns space mission design. So there are different types of space missions. You know that now NASA is planning to send people to the moon, and these are the type of space missions that need to take little time, a short time to go from the Earth to the moon and back. But there are other missions like robotic missions that are for research purposes that do not necessarily need a short time. So they may take weeks, months, or years. And there is a need that some of these robotic space missions should be done as efficiently as possible, and this is in terms of fuel consumption. So the cost of sending 1 pound of material to the moon, it's about $1 million. And I think this is an underestimate because the costs have been going up. So if you want to send a robotic mission to the moon, for example, you try to find ways to minimize the cost as much as possible. So I'm going to give a recent example of a research mission to the moon. So it was NASA's Grail lunar mission that happened between 2011 and 2012. So this was a mission to produce a high-resolution map of the moon gravitational field. And it was quite interesting. So it sent 2 satellites to the moon. So these satellites had to be placed more or less on the same orbit. So you see them in the picture. And they communicate to each other. So and they have a very precise way to detect each other's motion. So for instance, if there is a variation in the gravitational field of the moon and one of the satellites that is moving ahead is going down just a tiny little bit, then the other satellite would detect this motion. So in this way, by feeling each other, so to speak, and changing just a little bit the altitude of the orbit around the moon, they were able to detect even the smallest variation in the gravitational field of the moon. And when I say this motion can change a little bit, so the precision of this motion was about the thickness of the red blood cell. So extremely, extremely small. So they're extremely sensitive variations of the gravitational field of the moon. And there is so the trajectories to send this spacecraft to the moon were a little bit, let's say, unusual at the first sight. So here you see the Earth, and this is the orbit of the moon around the Earth. And here you see in red and blue the trajectories of the two spacecrafts. So there are actually two types of trajectory that could have been used. So in space mission design, people always need not one solution to a problem, but several solutions. Let's just say something goes wrong, so they need to figure out another solution to get to the moon. So that's why you see two sets of pairs of red and blue trajectories that go from the Earth to the moon. So again, red is for one satellite and blue is for the other satellite. So what is remarkable, so you'd say this is the Earth and this is the moon. And one way would be to just go more or less straight from the Earth to the moon. This is of course possible, but this is very costly. So it takes a lot of energy to design such a trajectory. So what you see here, it's a very strange type of trajectory. So you start from the Earth, you go towards the moon, but you pass by a lot the orbit of the moon. So you go actually towards the sun by a large distance. And by using the combined gravity of the sun, which is somewhere on the left of the picture, very far away, but it's a strong gravitational influence, and the gravitational field of the Earth and also of the moon, you have this sort of loop. The trajectory turns around on its own, essentially, and then it sort of comes back and it gets injected into an orbit around the moon. Along the motion, for a while, you see that the two spacecraft, the two satellites, share the same trajectory. At some point, they split, just very little. I mean, the picture is sort of exaggerated. And when they come back to the moon, they end up essentially on the same orbit around the moon as here. So why would you want to do that? The only objective is to minimize the energy consumption. So using the gravity of the Earth, Moon, and Sun helps you to save some of the energy, save some of the fuel for the mission.
So one question: the Earth liberation point 1 is the Earth-Sun liberation point, right?
So if the Earth-Sun liberation point, that is correct. So the Earth
Not the
is
Earth Moon.
Yes, that is correct. So this point, which we are going to discuss a little bit later, thank you very much for the question, Professor De La Llave. So this is like an equilibrium point, which is somewhere between Earth and Sun. So Sun is, as I said, somewhere far on the left. So you use for some part of the motion the Earth-Sun system, and then you get very close and you use for some other part of the motion the Earth-Moon system. And indeed, this point L1 that Professor De La Llave referred to is an equilibrium point for the Earth-Sun system. So it is good news that you save fuel. It is bad news that it takes a lot of time. So going from the Earth to the moon, if you use standard trajectory design, which is called Hoffman trajectory, this was used to send people to the moon. So that's more or less a 5-day trajectory. So this takes a short time, but it's not energy efficient. Such motions that use the sun and earth and the moon, like the one for the Grail mission, take somewhere between 6 to 9 months. So it's a lot of time, but they save energy. For robotic missions, this is not bad. So it's actually a benefit because when NASA designs such missions, they use them for different research purposes. It's not only to investigate the gravitational field of the moon, but to make some other observations, as well as to make adjustments. So they have to test their research equipment, they have to make necessary corrections to the trajectories. So the fact that they spend more time, it's not really too bad. So this is, again, so this is the way that NASA used to send people to the moon. So it's the trajectory, it's pretty much an arc of an ellipse. So first you have to put the spacecraft on an orbit around the Earth. So this is the circle around the Earth. Then you have to accelerate the motion. So you give an impulse here. And then the spacecraft will move on this elliptic arc and it will arrive somewhere close to the moon. So if you don't do anything, it will keep going on such an elliptic arc. But of course that you want to have, now you have to have a trajectory, an orbit around the moon. So then you have to slow down the motion. You slow down the motion, you apply an impulse in the opposite direction to slow down, to decelerate. And then you inject the spacecraft on an orbit of the moon. And then from this orbit around the moon, you can send another spacecraft with people to land on the moon. So this type of the motion requires to accelerate first, to put it on this elliptic orbit, and then slow down. So it requires at least 2 impulses, and this makes it not so much energy efficient. So there are other methods that can be used to design low energy space mission, and one of the first such missions was by my colleague at Yeshiva University at Belbruno, so who came up with this idea of weak stability boundary. And this one of the advantages of this method is to eliminate excess velocity. So it's what is called the ballistic capture. So it eliminates the need to slow down the trajectory as you approach the moon. And there are other type of methods to design low energy space missions. So they involve invariant manifolds, which I'm going to try to describe later. And these are methods that have been used. So the first use was weak stability boundary method was for a Japanese satellite mission to the moon in 1991. But NASA and European Space Agency use low energy space missions in several other situations. And there are actually not only several missions that use low energy, but I only have, let's say, I'm only mentioning just 2 of them. So the main objective of this lecture is how to find and also how to compute some geometric objects that help you to design low energy space missions. And the idea behind finding and computing these geometric objects is that they are determined by the gravitational fields of the Earth, Moon, or Earth, Sun, or a combination of them. So you start by understanding the differential equations that govern the motion of a spacecraft relative to the Earth, Moon, or Earth, Sun, and so on. Then you want to compute some geometric objects that organize the dynamics, that give you a sense of what kind of trajectories are possible. And then what you want is to pick some of these suitable trajectories for space missions. So this was the orbit for the Haiten Japanese space mission. So it's very similar to the one of Grail. So you want to go from the Earth to the Moon, and instead you go very far away and towards the Sun. So in this picture, the Sun is on the right. So you more or less go towards the Sun, you come back, and then the trajectory is inserted into an orbit around the Moon. So you may say, well, it's a nice trajectory. How do you get it? So in fact, you can find some geometric structures. So these are the green and red objects that appear in this computation. And you pretty much see that this trajectory of Haiten, it pretty much overlaps with a trajectory that follows this red cylinder. So if you just, so this is a picture that actually makes sense in 3 dimensions, but is projected onto the plane. So if you look a little bit, so it's like a circle, and there is a cylinder that is emerging out of the circle. So it's like a piece of a red cylinder. And here you have another piece of a green cylinder. So these are 2 geometric objects. They are cylinders, like not perfectly round cylinders, but nevertheless, cylinder looking like surfaces. And there is another green cylinder over here. And there are some other details that are hidden in this picture. So all I'm saying is that this trajectory that, for instance, Haiten mission used, you can decompose this trajectory into pieces of trajectory that follow these cylinders. These are some interesting geometric objects that I'm going to describe later. And these are the so-called invariant manifolds that I mentioned at the beginning of the talk. So I just would like to encourage everybody to ask questions. Please don't raise your hand. If you have a questions, please feel free to interrupt. I may not see if you raised your hand, and I'll be very happy to take questions as we go along. So, and I thank Professor Delshams for taking the lead in this aspect.
Yeah, I mean, we are among friends, so you are not going, I mean, now we are safe. You cannot be hit if you ask questions, so.
Absolutely. So just a brief description of what kind of mathematics has to be used to describe the motion of a spacecraft relative to Earth-Moon system. So really, you describe such motion through differential equations, through a system of differential equations. And these differential equations are the so-called Hamiltonian systems. So Hamiltonian systems are systems of differential equations that are encapsulated by a single function. So if you know this function, which is called the Hamiltonian, then you can write a system of differential equations and you solve it. And in the case of let's say the spacecraft trajectory, it will be a very particular Hamiltonian. And the Hamiltonian physically means the total energy of the system, which means, as it usually means in physics, kinetic plus potential energy. So if one gives you or derives this Hamiltonian function that has variables P and Q, Q stands for position, P stands for momentum, which is a proxy for velocity. So then the system of Hamiltonian equation is of the following form. P dot is negative partial derivative of the Hamiltonian with respect to Q. Q dot is a partial derivative of the Hamiltonian with respect to P. So each of these PQ are vectors in some dimension, 2, 3, and the dot means derivative with respect to time. So if this Hamiltonian function does not depend on time, which is what is called autonomous, then you have the law of energy conservation. So the energy, which is the Hamiltonian, is preserved along the solutions. So a general example of Hamiltonian systems, autonomous Hamiltonian systems. So autonomous again means the Hamiltonian function does not depend on time. The variable time does not appear in this function. Is when you have a mechanical system without dissipation. So you have kinetic energy plus potential energy. So typically, mechanical system without friction can be described like that. And this is indeed a good setup to study celestial mechanics, because out there in space, there is little to no friction, so you can use such mathematical models to describe that. So the objective is to talk about the three-body problem. So I'm not going to go over these equations in great detail. So it's really, you look at three bodies and you want to understand the motion of each of these bodies when they interact by gravity. So each body is affecting the others through a gravitational field. So what you get is, so the gravitation is the typical Newtonian gravitation. So the force is the gravitational force between two bodies inverse proportional to the distance squared. This is what is more or less said in this first equation. And when you write the corresponding equations of motion, you get a large system of equations. So in fact, you get 18 differential equations. So you may think 18 is a huge number. And of course, it's a huge number if you even think about solving such a system of differential equations by hand. Nobody does this anymore. So you just throw these equations into a computer, use the right numerical algorithms, and the fact that there are 18 differential equations doesn't bother you at all. And what is, sorry, I hit the mouse by accident. So this system of differential equation describing the relative motion of the bodies is a Hamiltonian system. So it's, you do an appropriate sort of change of coordinates or coordinate transformation, and you can write the motion of the three bodies as a Hamiltonian system, as we said before. So you have energy conservation. Not only that you have energy conservation, the total energy, kinetic plus potential, is conserved, but there are other quantities, physical quantities, that are also conserved by the motions, like linear momentum, the motion of the center of mass of the system, angular momentum, and so on. So there are 10 integrals of motion, 10 constant of motion, 10 quantities that are preserved along the solutions of the three-body problem. And these allow you to reduce the system from 18 equations to 8 equations, and you do some other tricks, and you actually reduce it to 6 equations. So it's not so bad. So when we talk about the three-body problem, if the system of equation is not integrable means that let's just say, you cannot express the solution in terms of, you cannot find closed form expressions of the solution in terms of typical functions that you use. I will say something more precise a couple of slides later. But if you talk about two-body problem, the two-body problem is integrable. You can solve the motion of two bodies, and this is in fact given by the Kepler's law. So I'm going to spend most of the time about the three-body problem. So you cannot really find nice solutions for the three-body problem. This is what it all says over here. And what I'm going to use is not just the three-body problem, but a simplified model of the three-body problem, which is called the restricted three-body problem. And the first model is the planar circular restricted three-body problem. So this says that two of the bodies, like Earth, Moon, or Sun, Earth, move on circular orbits around the center of mass of the system. From the Kepler's law, we know that the orbits can be circular or elliptic. So in this model, in the planar circular restricted three-body problem, we assume that the motion of the Earth around the Sun is circular. The other assumption is that the third body, which is the spacecraft, has a tiny mass and it does not affect the motion of the Earth and Moon. So this is a very reasonable assumption. I mean, in theory, even if you have a tiny mass, it can have a little effect. But the assumption is that it has absolutely no effect. So this stands for the word restricted. Circular, the orbits are circular, and planar, it means that the spacecraft will move in the same plane as the Sun and the Earth, or the Earth and the Moon. So typically, you want to choose a coordinate system that fixes the position of the Sun and the Earth, and study the motion of the spacecraft relative to this coordinate system. So the Sun and the Earth are on some horizontal axis, and the spacecraft is moving relative to this coordinate system. So this is what is called a co-rotating system. And to simplify the equations, you rescale all of the units. You don't work with the true mass of the Sun and the Earth, but you work with a relative mass ratio, which is the mass of the Earth divided by the sum of the mass of the Sun and the Earth. And then you get a Hamiltonian system that is autonomous. So there is no time in this formula for the Hamiltonian system. So the Hamiltonian system, again, it's more or less kinetic plus potential energy. Okay? So this is the planar circular restricted three-body problem, and it's a good model to study the motion of a spacecraft relative to Earth, Moon, Sun, Earth. So because the energy is conserved, when you fix an energy level, you get what is called a three-dimensional energy manifold. We are in the plane. So in the plane, and the equations concern the motion of the spacecraft. The motion of the spacecraft is described by two coordinates, x and y, because we are in the plane, and two velocity components. So you are in 4 dimensions, and the energy manifold means that you fix an energy level. So you put a restriction by a single equation on what kind of motions you're looking at. So when you put a single restrictions, you get a 3-dimensional manifold, which is the energy manifold. So it's a 3-dimensional manifold in a 4-dimensional space. So the picture on the top is just a cartoon. It's a projection of this into 3 dimensions. And you can further take the energy manifold and project it onto the XY coordinate space. So you imagine that you take this 3-dimensional picture and you project it onto the 2-dimensional plane, and you see some blue curves. So they divide the 2-dimensional plane into some regions, which are called hill regions. So hill region means that maybe the Earth is around 0, and the moon is around here, and the spacecraft is allowed to move around the Earth. I hope that you see the motion with my mouse. It can move around the moon. It can get out of this region and move around, but it cannot get into this thing that looks like a pretzel, that someone took a bite of the pretzel. So the hill region is the region of where motion can happen at this energy level, and it can happen around the Earth, it can happen around the moon, where it can go out and take big turns around this whole region. So this is where the motion of the spacecraft can take place for a given energy level. And if you change the energy level, this hill region also change. So for instance, in this panel up here, you can only move around the Earth or only around the moon, but you cannot pass between these two. So it means that if you want to send a spacecraft to the Earth, to the moon, you would not be able to use this energy level. You have to increase the energy level of the trajectory, like here, when it's possible to have a passage, a transfer between the Earth region and the moon region through this bottleneck over here. So looking further, so you have a system of differential equations, and when you, in the undergraduate class of differential equation, one way to understand what's going on is to look for equilibrium points. So you look for the equilibrium points and or rest points or fixed points. So it turns out that there are 5 of them for the restricted free-body problem, and they are called L1, L2, L3, L4, L5. 3 of them are on the line with the Earth and the moon, and 2 others are out of this horizontal line, and they form equilateral triangles with the Earth and the moon. They are all very useful because, for instance, if you wish to park a spacecraft in some more fixed position relative to the Earth and the moon, so each of them would be, let's just say, a candidate. However, L1, L2, and L3 are of center saddle type. So in other words, they are unstable. So if you try to place a spacecraft at L1, so it may stay there for a little while, but you know from differential equation, you have a center saddle type of equilibrium point. It's unstable. So that means that after a while, the spacecraft may escape from being staying at L1. So let me focus about this equilibrium point L1 because it's quite useful. That L1 and L2 are quite useful for space mission design. So not only that you have an equilibrium point at L1, which is an interesting object on its own, but you also have a family of periodic orbits around L1. So these are the blue orbits, and the red one are closed orbits, more or less elliptic around L1. So so if you wish to park a spacecraft, you can put it at L1, or even better, put it on one of these orbits around L1, and it will keep moving like that forever. These periodic orbits, they are called Lyapunov periodic orbits. They have stable and unstable directions, and they have what is called stable and unstable manifolds. So these are two-dimensional stable and unstable manifolds, or if you wish, surfaces that live in the three-dimensional energy manifold, which itself is contained in the four-dimensional phase space. So we've seen them before. They are these red and blue kind of cylinder-looking surfaces. So in this picture, the round or the black orbit here is the Lyapunov orbit. What you see here is the boundary of the Hill region. So the motion happens here around the moon and on the left around the Earth. This is the Lyapunov orbit. And you have these cylinders. The red is unstable manifold and the blue is stable manifold. What does it mean? It means that, for instance, if you put your spacecraft on the blue cylinder, the spacecraft will move by itself towards the Lyapunov orbit. So this takes zero cost. So this is good news. It means that you have some motions that require no fuel and they are generated just by the natural dynamics. So if you put it here on the red cylinder, you can start very close to the Lyapunov orbit and it will move on its own away. So this is the unstable manifold in the sense that it takes you away from the Lyapunov orbit towards the moon. The stable manifold takes you from the moon towards the Lyapunov orbit. And you see that these manifolds also have branches towards the Earth. So you can imagine all sorts of interesting motion. Maybe you're coming from the Earth on the blue manifold, on the blue cylinder. So you're coming from the Earth is on the left. You're coming on the blue manifold here. So you get very close to this Lyapunov orbit. You make a switch. You take the red one, you go towards the moon. Hopefully, if these manifolds will intersect, you make another switch and you take the stable manifold, the blue one, towards the Lyapunov orbit. You make another switch and so on. So in this way, using these manifolds, you can get trajectories that go around the Earth, they go around the moon, they go through this bottleneck, which is by the Lyapunov orbit, and all of these motions require zero energy cost. So you have interesting motions, interesting trajectories around the Earth and the moon at zero energy cost. So in order for this to be feasible, these red and blue manifolds should intersect, because if there is no intersection, you cannot switch from red to blue around this point. So, and it turns out that they do intersect. So this is, again, a projection onto the plane. So to find such intersections is not a very easy task, but one can do it. I'm going to try to explain a little bit how you can find such intersections. So, but once they intersect, you can complete the circuit. So you can take the unstable manifold, switch to the stable manifold, take the other unstable manifold from the previous unstable, switch to stable, take unstable, switch to stable. So you get interesting orbits that go around the Earth and go around the moon for free. So, by the way, whenever you have stable and unstable manifolds that intersect, there is a theorem in dynamical systems that you have lots of such orbits. So if you have one such orbit, when the stable and unstable manifold intersect in a transversal way, which means a non-trivial way, you find one intersection, which is called the homoclinic orbit, but the theory tells you that, in fact, you have infinitely many intersections. So you say, I want to find one such good spacecraft trajectory. If you find one, you find lots of them. And by the way, this theorem, it says that not only that you have infinitely many such orbits, which are called homoclinic orbits, but you also have chaotic dynamics. So chaotic dynamics, it means that you take two trajectories with nearby initial conditions, and they may have very different evolution in future time. So chaotic dynamics is actually what prevents the three-body problem to be integrable. So there is an argument which is a bit sophisticated. I can say that if you have chaotic motions, you cannot have the system cannot be integrable. So I mentioned before the three-body problem is not integrable. So the very fact that you have such manifolds that intersect transversally, it leads to an argument that the problem is not integrable. So now I can show you how to find that these manifolds intersect. So the stable and unstable manifolds are two-dimensional manifolds in a three-dimensional energy manifold. So in fact, if you see that the projections meet, it doesn't necessarily mean that in 3D or in 4D, these cylinders intersect. So what you have to do is take a slice in the space, which is called the Poincaré section, and find the intersection of the red cylinders, red tubes, and the blue tubes. And in the section, in the slice, when the red tubes and blue tubes intersect, you can confirm that you have an actually homoclinic trajectory. And you see in these pictures, which are done for different energy levels, you have lots of them. And there are many more than the eyes can see. So again, this is good news. So the theory is helping us to say that there are lots of homoclinic trajectories, and the numerics is also helping us to actually find explicitly these homoclinic trajectories. Again, homoclinic trajectories are good news because each homoclinic trajectory is a potential spacecraft trajectory that takes essentially no fuel. So, and now I can go back to this picture. This is the trajectory of the Japanese mission Haiten, and this can be explained using invariant manifolds, using stable and unstable manifolds. In fact, this is a bit more complicated because you are dealing with 4 bodies: Sun, Earth, Moon, and spacecraft. So you can think of it as you separate these into 2 problems. One is Sun, Earth, and spacecraft, and the other one is Earth, Moon, and spacecraft. And you use the stable and unstable manifolds for each of these problems. So here on the top panel, you use the Sun-Earth system. So the Earth is here, the Sun is to the left. This is L2, not L1. So we talked quite a bit about L1, but now I'm going to just say that L2 has similar properties as L1. So you start near the Earth, you follow the unstable manifold of the Lyapunov orbit L2 for the Sun-Earth system. This is the red one. And sorry, you follow the green one. Sorry, the color convention is different here. So green, it's the unstable, and no, the green is stable and red is the unstable. So you follow the green one, you go towards the Lyapunov orbit. You switch to the red one, which is the unstable. So you move away from the Lyapunov orbit. And now you switch to the Earth-Moon system. So the Earth-Moon system, so this is the Earth and the Moon is somewhere here. And this is a stable manifold for the L2 point of the Earth-Moon system. So you switch to this one, the stable manifold takes you to this Lyapunov orbit around L2 for the Earth-Moon system. And now the picture is tiny, so we magnify it and we look at the details, what happens around here. So you come like this, and in the picture at the bottom, it means that you come like that. So you go towards the L2 of the Earth-Moon system. You go towards the Moon. So this is where you can stop. So your mission took you. You started near the Earth. You went towards the Sun. You came back towards the Moon, and then you follow this trajectory, and you go very close to the Moon, and you can achieve ballistic capture in the sense that you don't have to fire the rocket to slow down the motion. So this is how you can explain this weak stability boundary concept using the invariant manifold. So the two methods are closely related to each other. And in the paper that I think I mentioned before by Belbruno, Topputo, and myself, so it is this picture here, this paper here, we sort of explain that this mechanism of weak stability boundary can be explained in terms of the invariant manifold. So now I think I have only 5 minutes, so I think I explained to some extent these invariant manifolds, the stable and unstable manifolds here. And now I'll go a little bit faster I'm not going to go into the details. So I'm just going to say that if you switch to a different model, which is called the spatial circular restrictive three-body problem. So instead of considering that the motion of the spacecraft happens in the same plane as the Sun and the Earth, or the Earth and the Moon, you consider that the motion of the spacecraft can happen outside of this plane. So this is the spatial circular restrictive three-body problem. So this can be also described by a Hamiltonian. You also look for the equilibrium points, which are the same. But now around L1, instead of having just Lyapunov orbits, just periodic orbits, we have more complicated orbits. So you can find some invariant tori. So you have these invariant tori, which are in blue and in green. So these have also stable and unstable manifolds. And it turns out that you can move from one torus to another. So I'm going to skip some of the slides. And I'm going to go right here. So you had a green torus and you have a blue torus. And you just use the natural dynamics and the invariant manifolds, the stable and unstable manifolds associated to these tori. Now these are objects that have 3 dimensions as opposed to 2 dimensions. So in the previous case, we had those cylinders that were 2-dimensional. For the tori, the stable and unstable manifolds are 3-dimensional. The whole computation gets a bit more complicated, but still you do it with the computer, so it can be done, so to speak. And what happens is that you can use these stable and unstable manifolds to move from one torus, the green one, to the blue torus. What does it achieve for us? Let me switch back. So you see that the blue torus is kind of flat. and the green torus is taller. What does it mean? It means that the blue trajectory, if you are on the blue torus, the trajectory of the spacecraft is almost planar. It's a little bit off the plane. But if you are on the green torus, the trajectory of the spacecraft is much more inclined. And quick switch, what you achieve is that for free, without consuming any energy at all, you can switch from one torus to another, which means you can change the inclination of the orbit of the satellite at zero cost. So going back to the planar problem, what I started was to say that the first method was the planar circular restricted free-body problem, which assumes that the motion of the planet around the sun is circular. This is a good approximation for some planets, for instance, for the motion of the Earth around the sun. But for some others, the Keplerian orbit is truly elliptic, and it has some eccentricity, which, even though it's small, it's not negligible. So Sun-Jupiter system, the orbit of Jupiter around the sun has eccentricity which is almost 0.05. It's not a lot, but it's something, and you want to take this into account. So in this case, we can still use stable and unstable manifolds to move from a Lyapunov orbit to another Lyapunov orbit at no cost. So remember, in the spatial problem, we are moving from one torus to another torus at no cost. In this planar elliptic restricted free-body problem, we can move from a Lyapunov orbit, from a periodic orbit around L1 to another periodic orbit around L1 at no cost. But this time you exploit the eccentricity of the orbit of Jupiter around the sun, and the eccentricity is like a bit of forcing. So if you know how to use this forcing in a smart way, you can achieve such motions that take you from a small orbit around L1 to a larger orbit around L1. And this has been done in a paper by Professor Kapinski, Professor Yave. So I'm going to end in finish with this slide. So maybe I take another minute from your generous time. So these orbits that I described are zero energy. So you don't have to fire the rocket at all, in theory. Of course, that you can, in real life, you may need to make some corrections of the trajectory. So you may fire the rockets a little bit in order to adjust the trajectory if it was a little bit off. The other aspect is that these can be very small, these trajectories can be very slow. So for instance, if you want to switch from the green torus to the red torus, you see that you go away and you come back, but you spend a lot of time moving on this tori in order to make the next jump. So here, if you are willing to fire the rocket, you can sort of take shortcuts. So instead of doing this very, very slow motion at zero energy cost, you fire the rocket and you sort of quickly go where you are supposed to make the next move. So instead of moving around like forever, you fire the rocket and you go right away. So going from zero energy to low cost energy, it's very nice to do. I mean, in real life, you will spend a little bit of fuel anyhow. And if you choose the right place and the right time to fire the rocket, you still save a lot of fuel, but you also can save a lot of time. And I'm going to stop here, and I'm just going to mention some of the computational resources that can be used to compute these trajectories and these geometric objects. So some of them are on Professor James' webpage. So here's a MATLAB code with instructions. So it's not so hard for undergraduate students to just follow the instructions and run simulations right away. And there is a more sophisticated package, computer-assisted proofs in dynamics. So all of these are hyperlinks. So if you click on this, it takes you to Professor Mireles' webpage or to CAPD webpage. So all of these have plenty of instructions, examples, documentations, and anything you want to jumpstart computations of such trajectories and of the invariant objects. Thank you very much. Sorry for taking some extra minutes. But, Jorge told me that it's
No
not
problem.
totally forbidden to do that. So thank you.
Thank you very much. I think we have time for maybe one question. I will stop the recording in case some people are shy like me.